This is 301.2, second law in FBD's problem set. We're going to work through the questions on it so that we can hopefully answer any problems that you might have. The first one says, you just ran out of gas and your car is moving to the right and coasting to a stop. Identify the appropriate free body diagram for this situation. When you draw a free body diagram, you need to make sure to include all of the forces acting on the system. Okay, so for this example, we know that we're going to have gravity because we're on Earth. We also know we're going to have normal force because the car is coasting along a roadway. So there's going to be a support force from that. It's not accelerating up or down. So I know that there is some kind of force countering that force of gravity. In this particular question, since it says we're coasting to a stop, I know that there must be some kind of force moving in the opposite direction as the car that's causing it to slow down. The most logical explanation would be friction. Moving and coasting to a stop would be due to friction acting on the car. And so if we take a look at these free body diagrams, there are several of them that have friction, B, C, and E in this particular question. All have friction on them along with gravity and normal force. The thing that differentiates these is the applied force that is present in these two, that is not present here. And then of course between these two, these have equal vectors and these don't. And so taking a look at this, it says that our car ran out of gas and it's just coasting to a stop. So the car is already moving. It's already moving to the right. There's not a force being applied to make it move. It's just going that way. The force that's applied is against the car, bringing it to a stop. And so the diagram that shows that is diagram B. Again, you don't have to have a force in the forward direction in order to have a situation with the car moving that way. It was already going that way when it ran out of gas, and so it's still moving that way, but there's no longer an applied force from the engine. Now it's just friction. Come on. Question 2 on the assignment 301.2 says a crate is being pushed to the right against friction. The crate accelerates. Identify the appropriate free body diagram for the situation. Again, we're going to have gravity every time. It's in all of the diagrams. We're also going to have normal force because this crate is being pushed across some type of surface. I know that because, well, it makes sense for it to be pushed across a surface. You can't push something without a surface like that. But secondly, it says that there's friction. It's being pushed against friction. Friction implies that there are two surfaces rubbing against one another. So I know that I need gravity down and normal force up. I can eliminate this one right here because that shows an object that is basically in free fall. In this example, it says it's being pushed to the right, so we do need to have a force to the right that is an applied force, which means that we are left choosing between this one and this one. Those have applied forces to the right. The only difference between these two free body diagrams is the length of the friction vector. In the one on the top, the amount of friction is equal to the force that is applied. In the one on the bottom, or underneath it, the amount of applied force is greater than the force of friction. And so we need to choose it according to the scenario. In this particular question, it states that the crate accelerates. In order for the crate to accelerate, I must have a net force acting on the crate. I can't have these cancel out with no net force. I have to have them varying lengths. This one has to be longer than this one so that I have a net force so that I have acceleration. So the answer to the second question should be this diagram right here. The third question in this problem set states, what is the net force on an object if its mass is 67.1 kilograms and its acceleration is 6.05 meters per second to the west? In this particular question, we are going to be going back to the same equation that we have been using for this entire unit. F net equals m times a. Okay, so we have net force equals mass times acceleration. It says what is the net force? We're going to be solving for F net. The mass that is given to us, F net equals, the mass is 67.1 kilograms times the acceleration given to us is 6.05 meters per second. All we have to do is multiply those two values. So let's go ahead and do that. 67.1 times 6.05 gives me a value of 405.955, and you can type that whole number out, but you only have to have 2 decimals. That would make it 96. So it's up to you if you round that or not. The unit, sorry, I'm not trying to zoom. The unit that we need for force is the Newton, and the direction of my net force is always in the same direction as my acceleration. My acceleration is to the west, therefore my net force must be to the west. Question number 4 in the assignment 301.2. If an object is accelerating at 8.24 meters per second to the west due to it experiencing a net force of 707 newtons to the west, then what is the mass of the object? Very similar question, except this time they gave us a net force and they gave us an acceleration and we're solving for m. But it's the same equation. So let's go ahead and put in the numbers. I'm going to write it down here and plug it into that formula. Net force is 707 newtons. It is equal to, my mass is what I'm trying to find, times the acceleration, which in this case is 8.24. Okay, and so that is my substitution step. Again, I'm trying to solve for this mass, which means I need to isolate that variable. These are being multiplied, so we're going to divide both sides by 8.24. That's going to cancel over here, and on this side I'm going to take on my calculator, 707 divided by 8.24, and that will give me my mass. Again, I only have to have 2 decimal places according to the directions for these assignments, so 85.80 is fine. The units for mass will be kilograms, and the direction. Mass does not have a direction. It is scalar, so we're going to select that from the options. Question 5 from the assignment 301.2 says, in a lab, a block weighing 68.6 newtons is attached to a spring scale, and both are pulled to the right on a horizontal surface as shown above. Friction between the block and the surface is negligible. What is the acceleration of the block when the scale reads 14 newtons? So before I can actually solve this problem, and anytime you're trying to work out a problem like this, where you have a lot of information, start with a free body diagram. I know looking at this that I have many forces acting on the block. Ultimately, I do need to be examining the forces on the block because I'm looking for the acceleration of the block. So I want to know what forces are acting on it. I know that I always draw in force of gravity, which is the weight of this block. I also know the weight was given to me in the question, a block weighing 68.6 newtons. It's right there. So I don't have to solve for it. I'm just going to copy it down. 68.6 newtons, that is my weight, my FG. Okay, now sometimes it's not worded like this. It'll say a 68.6 Newton block. And if it's listed that way, it's still the weight because it's listing this as a property of the block. And again, newtons is a unit of force. And so if the property that we're talking about is a force, then it's going to be the weight. It's not what it's being pushed or pulled with. That's down here. Okay, so this is the weight. Now, as this thing is being pulled, it's going to the right on this horizontal surface. There's no motion up or down. There's certainly no acceleration up or down. And so I know that in the vertical direction, I need to have forces that are balanced. I need to have an upward force that is equal and opposite to this downward force. And that force is going to be the support force, Fn, from this surface, this table or floor or whatever it is. And so the value for Fn will be equal and opposite to the value for Fg. So this 68.6, I'm also going to write it up here. .6 newtons. The only other force that I have is the fact that this spring scale is pulling this block, and the spring scale reads 14 newtons. If that's what the spring scale reads, that makes that my applied force. And so I have this force being applied in this direction. with a value of 14 newtons. I don't need to include friction because it says that friction is negligible. That just means that it's so small that we can ignore it. Okay, so from here we're looking for acceleration. It's the same equation we've been using. F net equals m times a. That's how I find acceleration, which means I need a net force and I need a mass. Looking at the question, I can see the net force. Really, I see it in my picture. This is my net force because these two forces cancel each other out. Okay, so the only force remaining that's not canceled out is this one. So I have F net. It happens to equal Fa, which is 14 newtons. I don't, however, have the mass that I need in order to solve this. Again, F net is ma. If I want to find A, I need the mass as well. I do, however, have the weight. And if I have weight, I can find mass because I know that the weight of an object is equal to its mass times acceleration due to gravity. And on Earth, acceleration due to gravity is negative 9.8. And so I can solve for the mass using the weight. The weight is negative 68.6 newtons. And it's negative because it is a downward force. The Earth pulls down on you. Forces are vectors, so I'm going to put the negative in there. Equals mass times negative 9.8. If I want to solve for mass, I need it by itself. I need to divide both sides by negative 9.8. And so that's what's going to go in my calculator. These negatives are going to cancel, so it's really just 68.7 divided by 9.8. It's where we can see it all. 68.7 divided by 9.8, and that gives me my mass 7.01. Sorry, that's not my answer, that's my mass. So let's go ahead and label it. M 7.01 kilograms. Okay, so we have our mass, we have F net. We can now use these to solve for acceleration, which is what the question is asking for. So F net equals ma. Let's substitute in. F net is 14. It is equal to mass times acceleration, or sorry, mass in this case is not m, it's 7.01. We found that a second ago, times a. We're looking for a. I need to divide both sides by 7.01. I know this is going to be about 2 because this is about 14 divided by 7, but let's see if we have to worry about a decimal. 1.997 to 2 decimal places. If I round that, 1.99 ends up rounding up to 2.00, so I can just call that 2. You shouldn't even have to type the decimals because if there's zeros, it won't make you type them. Acceleration is in units of meters per second squared. All right, this is number 6. So let's take a look at how we can solve this problem. It says, Thomas and Kelsey apply a 108.7 Newton force to the left when moving a 54.5 kilogram sofa, causing it to accelerate across a frictionless floor. Again, we're going to start with a free body diagram. That's my sofa. Looks very much like a sofa. I know that they are going to apply a force to the left. It says so in the question. So let's go ahead and draw a vector to the left. It is 108.7 newtons, and that's my applied force. I know that, again, I have a sofa. I'm on Earth. I have Fg. Fg is the weight of the sofa. Okay, it is equal to mass times gravitational acceleration. I also know that my sofa is moving to the left. Okay, they're applying the force, causing it to accelerate across the floor. So it sounds like it was at rest, and then they pushed it to the left and made it move. And that would, of course, would make it accelerate. And so I know that I'm on a surface. I'm on the floor. I don't have acceleration up or down. I don't even have movement up or down. So there's no acceleration up or down, which means in the vertical direction, my forces need to be balanced. They have to cancel each other out. That upward support force from the floor is called Fn, and it will be equal and opposite to Fg. So, if I want to solve for the acceleration of the sofa, again, here's my free body diagram, but ultimately I'm going to go back to this equation. F net equals m times a. And I'll be looking for a, which means I need F net, and I can actually see that in my image already over here. This will be my net force because those cancel out, and that's the only thing that doesn't cancel. So that will be F net, and then my mass is in the question. So let's go ahead and plug these numbers in. 108.7 equals, my mass is 54.5 times A. And again, if I want to solve for A, I'm going to divide both sides by 54.5. That's going to cancel it here, and then that's what's going to go in my calculator. 108.7 divided by 54.5 gives me an acceleration of 1.9944, and it keeps going, but this one will be 1.99 to 2 decimals. The unit for acceleration will be meters per second, and the direction of the acceleration is always in the direction of the net force. I can see it in my picture. It's to the left. It's also written in the question, to the left. So let's go ahead and use the same terminology that's in the question, left, since that's what's up here, and we'll type it here. If it says south up here, you'd want to type south. Make sure you match the same direction that's given to you. The second part of the question says, if they then use the same amount of force to move another piece of furniture with half the mass, how will its acceleration compare? Okay, so again, we talked about this in class, but think about it logically. If you were to push two objects, one of them with a lot more mass than the other, the example I used in class was, hey, what if you pushed like a high school football player and then like an elementary school girl? Okay, maybe she has half the mass that he does. Who's going to accelerate more? If you push them both with the same force, you should already know that the girl will accelerate a lot more than that football player. Okay, so if you have less mass, you're going to have greater acceleration. That allows me to eliminate all of those. Okay, I want more acceleration when I have half the mass. And if I have half the mass, I would have 2 times the acceleration because the relationship between mass and acceleration is inversely proportional. Look at the equation, you can see it this way too. If the force stays the same, then these things still have to multiply to be the same number. If you end up with less mass, you would have to have a greater acceleration by an equal factor in order to maintain the same force. The opposite is also true, but it should be 2 times as much. This is question 7 in the assignment 301.2. It says, analyze the graph below to answer the following questions. This is a velocity time graph. It asks us, during which sections of the graph is the net force acting upon the object a non-zero value? In other words, where do I have a net force? Where are my forces not all canceling? And when I have that net force, when it isn't a 0, that means that I have acceleration. And so that's really what you're looking for. Because on a velocity time graph, you can't see forces, but you can absolutely see acceleration. We talked about this in the last unit. On a velocity time graph, acceleration is your slope. So you are looking for sections of the graph where your slope is not 0, where you have a slope. For example, if I look at this blue section up here that is horizontal, this represents a period of time where I have a constant velocity, specifically of 15 meters per second, but I have constant velocity. That would only happen if my net force was 0. That's why I'm looking for non-zero. Okay, and so I don't want to pick this one. Instead, I want to pick regions of my graph like this first black line segment where I have a slope. This is a non-zero slope, and thus it is a non-zero acceleration, which means it's a non-zero force. Okay, so again, if I'm looking for a net force, that means I'm looking for places where I have acceleration. On a VT graph, that means I'm looking for a slope that isn't 0. That's going to be this black portion, that's going to be this green portion right here, it's going to be this red portion, and it's going to be the last section that's purple. Okay, so black, green, red, purple. The blue, the orange or yellow, and this darker red, or brown I guess is what it's called, those are all zero slope, and therefore they are constant velocity. We don't want to choose those. All right, question 8. Question 8 says, box 1 has a mass of 9 kilograms and accelerates at 9 meters per second squared. Box 2 has a mass of 9 kilograms and accelerates at 5 meters per second squared. Box 3 has a mass of 5 kilograms and accelerates at 5 meters per second squared. What is the net force acting on each box? Net force is still mass times acceleration. This is really easy. Here's a mass, here's an acceleration for box 1. All I'm going to do is multiply them. 9 times 9 is 81. The unit we use for force is the Newton. For box 2, 9 times 5 is 45. Again, the unit is the Newton. For box 3, there's my mass, 5. There's my acceleration, 5. That's 25 newtons. Very similar to the last question. Different numbers, but question 9 is going to have you do that same process, but then you're going to choose which box has the greatest net force. So if I take a look at these, my first box, box 1, with a mass of 5 and an acceleration of 6, has a net force of 30. Box 2 is less. 6 times 4 is 24. In box 3, I don't even have to do that math because 10 times 9 is by far bigger than any of the other things up here. So in my particular example, box 3 with a mass of 10 and an acceleration of 9 meters per second squared has the largest net force, in my case 90 newtons. All right, this is the last question on your assignment, and it says, what is the net force on the object below? So this is a free body diagram, and I have an upward force of 385 newtons and a downward force of 77 newtons. The net force is the sum of the forces acting on the object, but keep in mind forces are vectors. So my net force, F net, equals any of those forces that are going upward in this case, plus any of the forces going down. That's how I'm going to solve for my net force, at least vertically. Of course, if I had horizontal forces, I would be adding forces to the left plus forces to the right. I don't have that here. So again, keeping in mind that forces are vectors. So when I add this, my upward force is positive 385 plus my downward force is negative 77. So I end up subtracting, and I didn't really have to write this plus sign. It's basically 385 minus 77. That's what's going to give us our net force. 385 minus 77 is 308. And so my net force would be 308 newtons. And you'll notice that my answer is a positive number, and it's positive because this force is a lot bigger than this one. Okay, in fact, it's this much bigger, 308 newtons. So my magnitude of net force, 308. My unit, newtons. The direction of my net force is upward. If your downward vector is bigger, then your direction will be downward. You don't have to type the negative, it just asks for magnitude. You would select the direction here. The only reason you would choose no direction is if you received a free body diagram with equal and opposite forces. If these were both 77. Okay, then I would have to say no direction because my net force would end up being 0. But in my case, it's 308 newtons upward. So that is how you work out the problems on 301.2.